Okay, so we're going to start chapter 11, which is all about dynamic measurements. So the one thing is that when we've been going through this class is that, we assume we have some measurand, right? Temperature, pressure, humidity, what else? Displacement, velocity, any of the measurements that we want to make. And we have some sort of sensor. And for purposes of controls that you're more than likely going to take after this class, I'm going to make the sensor H, okay? And the output of this is some signal, and it's typically voltage. And that is going to go through some filter. It could be an op-amp, amplifier, a low-pass filter, a high-pass filter, something like that. And so you're going to have a filter here, and I'm actually going to call this H1, and I'm going to call this H2 here. Okay, and so you have like your actual sensing element that responds to it. So like if you have a thermocouple, right, the voltage is going to change based on temperature. If you have a pitot probe, you're going to have a pressure transducer where the voltage is going to change based on pressure, which is really a strain gauge, but anyway. The output of here is going to be sort of your conditioned signal, okay? And then that is going to go through your data acquisition system, which is going to output a number in binary. So this is going to be your A to D, so it's going to be, n bit A to D with some sampling frequency. And when we talk about chapter 5, we're going to talk about why sampling frequency is really important, because you need to make sure that you sample your data quick enough. But in this case, for now, I want to talk about how this all works in real time, right? So a lot of times what we assume is that all of these equations are linear, and so if you take the example of the pitot probe and the pressure transducer, this output voltage here is going to be voltage is equal to pressure. Actually, I think it's the other way around. Yeah, voltage is equal to 101.325 times pressure. And so as the pressure changes, and I think this is pressure in atmospheres, and this is voltage in volts, okay? And so if you have a pressure transducer here with an input, let me put the input ports down here. If I have a P naught and a P infinity, and I have a strain gauge here, right? And this is going to output a voltage. If the pressure in the stagnation port increases and stretches the strain gauge, it's going to output a voltage, and it's going to be proportional to this. And this is linear, right? When we do our signal conditioning here, when we did, like, say, the Butterworth filters, right? We were assuming steady state. And that is when we drew the Bode plot, right, and we drew gain and input frequency, we were assuming that, most of the area of interest that we were looking at was over here, where the frequency was low. So this is like, you're flying in an airplane and the velocity is not changing that drastically. And so we were assuming, this is sort of your, what is this thing called? It's called your DC gain. And it makes sense because it's basically saying this is like a direct current gain that you're looking at. Everything over here, the reason why we have it roll off at some cutoff frequency is because we assume that this out here is noise. And we assume this happens instantaneously. We also assume that this happens instantaneously. When we create these linear equations and these equations here, we just assume that they kind of just go through these filters and they happen automatically. Even this over here, computers nowadays are super fast, and these take on the order of nanoseconds to get data. But you have to understand that every single thing in here is going to trickle in some delay, right? If you look at your standard Butterworth filter, right, your Butterworth filter has resistors and it's got a capacitor in there, right? And here's your op amp. This might be a high pass filter, but it's irrelevant. The point is that this capacitor, if you recall, the voltage across a capacitor is equal to, the current is equal to C times dV dt, right? And so the current running through this capacitor is actually a differential equation. And so if you build a Butterworth filter, you're going to introduce some delay, and your measurand is actually going to lag behind your data, okay? And not only that, your measurement itself might take time to respond. And if you put this all together, and you just make this one huge big loop, and just call this H, just capital H, so this is like H1, H2, and that's like H3, you can assume that your input, I'm going to say temperature in this case, is T, and my sensor block, okay, is H. My output, I'm going to call T tilde, which is my measured signal. And that measured signal is going to have noise, delay, scale factor, bias, all of the different things, cross sensitivities, and they're all going to be embedded in this. Now, in the past, we may have assumed that this was linear, but what we're now going to do is assume this is dynamic. And the best example I can describe is, imagine you are in your house and you've AC'd the house down to 68 degrees. Somehow you have an awesome AC system. And you have a temperature sensor that's reading 68 degrees. Outside, you're living in the south, and it's 95 degrees. If you take that temperature sensor and just open your door and immediately walk outside, your temperature reading is not going to read 95 degrees. It is going to take time to slowly ramp up, okay? And if you plot your temperature as a function of time, your initial condition is going to be 68 degrees, but it's going to slowly ramp up to 95 degrees Fahrenheit. And somewhere in here, you're going to be pretty much within, say, 2%. And this is what we call our settling time, okay? And so what we really care about for a system is how long does it take for the sensor to settle before I can move on, okay? And at least for this chapter, we're going to go over first order dynamic systems, and then we're going to go over second order dynamic systems. We're just going to do very, very high level first order and second order systems. You're going to see a lot more of this in other classes like controls and things like that. So we're going to do a temperature example, which is first order, and then we're going to do an accelerometer, which is second order. And just to make sure these videos aren't too long, I'm going to go ahead and put both of those examples in a different video.